How's it going, everyone? Today's video is going to be about another flash device, which is a Lexar USB thumb drive. This drive has gone to a few different shops, and they've tried swapping the controller. Swapping the controller is not really, it doesn't really work, and it's not like working on a hard drive where where we find the donor drive and we swap the heads or whatever. It's not that easy, unfortunately. You might have two identical controllers that look the same, even if you can find it. Actually, if you can find an identical controller, it doesn't actually mean it's going to be identical, because the software revision could be different, which is the firmware. And a lot of times what actually fails in a thumb drive is not the controller itself. It could be the translation table on the NAND. So swapping the controller is just a big waste of time. But that's one problem. Another problem is, you can create another problem by swapping the controller. It could actually cause an issue with the memory. So this is why we don't do it. It's actually better to use a proper tool like Visual Nand Reconstructor, which is what we use here, and that's what we use to recover the data. Anyway, so let's go have a look at it on the microscope and see what it looks like. Okay, so here's the USB drive. I don't know if it was this bent when the other shop first received it, but it's obviously bent. From what I was told, this particular drive wasn't working, so my guess was it was the controller from the get-go. So you can see a leg missing here. So not only that, they torched this controller. I mean, this is probably burnt flux. There's a lot of flux on here. I don't know what kind of flux they're using, but it's definitely not MTEC or whatever. What else? We already removed the chips. The chips are here. Your standard TSOP chips. I mean, we're not gonna film chip removal. We already done this in other cases. But yeah. So I'm just wondering. I wonder if this flash drive was damaged, physically damaged from the get-go, or was it bent and melted? You can see it's melted a little bit and broken inside here. So it's kind of hard to say. But in any case, this case is already done. We're gonna go over now to Visual Nand Reconstructor. I'm gonna go step by step and explain how we recover this data. So let's go over there now. So here we are in VNR, the Visual Nand Reconstructor. So every case begins with just a reader element. These elements are not visible because they're not there when you first start. You actually have to build this. What VNR consists of is rebuilding the chip, the memory chip, and putting it together, specifying data areas, ECC, or any other areas that are on the raw memory. All you're getting is real access to the actual raw memory. You don't really get access to the file system. You have to rebuild it. So first thing we do is we pop it in the reader, and then we go read memory, read ID. And if you clean the chip correctly and the chip is in the cradle the right way, obviously you're gonna get the crystal. Some chips have more than one. If you watch some of our other videos, you'll see some chips have more than one. So anyways, so that's that. So then you dump it into two separate dumps. These are two separate chips, and once that is done, you can go into the dump viewer. Let's go back to the beginning here. And then in dump viewer, you can actually examine the chip here and look at the raw data. None of this is usable at the moment. All this is just garbage. It's probably scrambled. It's probably XOR'd. So you don't actually see patterns. When you finally get the data correctly, this noise that you just saw, this noise will eventually become a visible data. Well, not visible, but you're gonna see lines coming across. So the way we built this is we have to specify data areas and ECC. So we know on this particular SM controller that the data is split into 1024 by 8 and 88 for ECC. So that's what's happening here. You see one by one, and if you scroll across here, you can actually see it. There was ECC there. Let me just go back a little bit here. There's ECC. When you get to the end, you're gonna see all this here. This is usually reserved for system area, and like I said, this is only for this particular controller. Every controller is different. So the system area in this particular controller consists of the header and LBN. Some have other options, but in this particular case, that's what we have to do. And you can tell LBN and the headers by these vertical lines, wherever there's data. Okay, so once we have these, we're going to put in our error correction through BCH. We have to put in the correct code words. In this case, these are the settings in this particular chip. Every chip is different, so sometimes BCH can detect automatically. If not, you can do this by hand. There is some math involved in this, which I'm not going to go over because this video would be too long. But once you do that, you can actually view the map. And here's the map of the BCH. Let me just find some areas. So anywhere you see light green, this is area that can be corrected by BCH. And usually when we are working on a recovery, we leave BCH off. The reason is, otherwise it would be the whole process would be very, very slow. So BCH is off all the way until we get to the logical image. So because we knew how the patterns were set up on this chip, we figured out that this data was XORed. XOR means it's been scrambled. So what happens is data is scrambled on the chip. That thing is a low-level encryption, so it's we actually had keys for this particular chip, so we're able to load this for SM, which is silicon motion. This settings for this. This is actually not the same controller that's on the USB drive, but this is the closest one I could find that was actually working. Once you get to that point, you unite these two, the dumps. You build your markers table, and markers tables. There's a little bit of work involved in markers tables. You have to unselect a lot of garbage data. That's not. You have to sort this, and this will take some time as well. Once you get past with that, you can build your logical image, and once you have your logical image, if everything is correct, if all the components and all the settings are correct in this image, in this dump, then you actually get the file system. In our case, there have been some files that are not recovered, like these ones here with the red flag. That can be sometimes corrected using a bit verification. We haven't run it yet because the customer doesn't really care about these files. So if he chooses to go and want us to fix it, we can probably run bit verification, and hopefully we will be able to get those files. But this is the gist of using VNR. I mean, it looks fairly simple here, but there are cases that are way more complex and take a very long time to decode. And some chips cannot be done at all. So, for the amount of money we spend on these drives, we don't realize how much work is actually involved in recovering this data and just looking at the VNR output. This is one of them. I would invite some of you go look at ruSolut's website and actually have a look at some of their case studies there. They have all different kinds of cases that they've done. You can actually see how complex some drives can get. Solid-state drives are very complex as well. But anyways, I hope you guys enjoyed this video. This is it for this one. We hope to have another one coming up soon, so please stay tuned. Thank you for watching.